of this lesson. Shaunak, can you take over?
Yeah. So welcome everyone. We have Professor Patrick Allen from McGill University. He'll be talking about modularity over totally real fields. So I'm going to hand it over to him. So over to you, Patrick.
Okay, thank you for the introduction, but also the invitation to speak here. Thank you everybody also for showing up to my talk. So as I mentioned, so this is going to be a sort of an expository talk just about what it means for an elliptic curve to be modular over a totally real field. In particular, I'm not going to talk at all about results proving modularity or anything like that. I just want to describe what it means. And in order to do so, I mean, it's best to recall the situation over Q. So I'm going to do this very quickly because I saw that there were a couple lectures previously by Shaunak explaining this quite well. So let's just go back and recap very quickly what the situation is. So let's say I have an elliptic curve over Q. So we say E is modular if one, but then what's the non-trivial thing is that all of what I'm going to say are equivalent any of the following, equivalent conditions are satisfied. So one version of modularity, so I'm going to use sort of similar terminology to Shaunak did, I'll call it version X, is that there exists a surjective morphism X not N to E of curves over Q, where here N is the conductor of E, and X naught of N is the compactified modular curve. So right, this is Y naught of N bar, compact modular curve with whose complex points are easily described as being the upper half plane modulo the congruent subgroup. Actually, maybe I'll put my quotient on the other side. So the congruent subgroup acts on the upper half plane, gamma naught N, and I take the quotient. Okay, so this is one version of being modular. There's also what I'll call version J, which is that there exists a surjective morphism of abelian varieties over Q from the Jacobian of this modular curve to E, where J naught of N is just my notation for the Jacobian of X naught of N. Okay, so this is another version. Yet another that I'll call version L. Now I think Shaunak maybe called this version AP when he talked about this, but I want to call it version L because I want to think of it as being the L function. That's the, so there exists a new form F of weight 2 level gamma 0 N such that we have an equality of L functions. The L function of E is equal to, well, maybe let me move this down, such that the L function of E is equal to the L function of F. Okay, and then closely related to this is what I'll call version G. Extra space here. G for Galois is that, again, similarly, there exists a new form, F inside S2 gamma 0 n, such that I'm going to say rho EL is isomorphic to rho FL for some equivalently any prime L. Or what is this rho? Where rho question mark L is the L-adic Galois representation. Gal Q bar over Q to GL2. Let me write it, go into QL bar associated to question mark, whether it's E or F. Okay, so these are the four versions that I want to sort of introduce right now. And what I want to do for this talk is discuss let's sort of recap. What's the purpose of my talk? My purpose of this talk is to define what it means to be modular over totally real fields. And so I want to recall all the possible versions over Q. They're sort of all known to be equivalent. And then we're going to see how these things generalize and whether they make sense or not. Okay. Are there any questions so far? Feel free to interrupt me, please, if you have questions.
X stand for?
Pardon?
What do L, G, and X?
Oh, yeah, so X is just common notation for this curve.
Okay.
This is what we usually use X to denote this curve. And then J stands for Jacobian, L for L function, and I'd use G for Galois. This is non-standard notation. This is just a way to.
Good.
Yeah.
But it means something.
Yeah, I just told, yeah, exactly. That's just, but it means something in my head. It's not, yeah. So you won't find this necessarily somewhere else in literature. Okay. Okay, so let me say, why are these equivalent? Let me briefly recall this because this will play a role in what I'm talking about later. So first, let me just say that the equivalence of X and J is essentially tautological. This is just because that there exists, the way the Jacobian is formed, there exists a map from X naught of n to J naught of n. It sends the cusp at infinity to the zero element, is universal for morphisms from X naught of n to an abelian variety A, such that it sends this cusp to the zero element. So it's really just because this is the universal property of the Jacobian, it's basically tautological that a map from X naught to the elliptic curve is equivalent to a map from the Jacobian to the elliptic curve. That's immediate. Okay, something that's a little bit less tautological, but is also kind of standard, is the equivalence of the L function in the Galois definition. And that's because if, let's say, P doesn't divide N, then we know that on one hand, the trace of the Galois representation, so remember, N is a conductor of E. So we know that this is unramified and that the trace of Frobenius is AP of E, where AP of E is a standard number that is P plus 1 minus the number of points on the mod P reduction of E. Okay. On the other hand, on the modular form side, it's again unramified, and its trace of Frobenius is AP of F, or AP of F is equal to the eigenvalue of the Hecke operator TP on F. Okay, and let's recall, we also have that the local L functions are given by exactly the same data. So for the elliptic curve at P, this is 1 minus AP of E, P to the negative S, plus P to the 1 minus 2S inverse. And the L function at P of F is equal to 1 minus AP of F, P to the negative S, plus P 1 minus, minus 2S inverse. Okay, so at least right? On the surface, the reason why these two things are equivalent is that, let's just look at P naught dividing N. They're both just equivalent to understanding these numbers. So this local L factor being equal to this local L factor is the same thing as saying that the Galois representation on Frobenius has the same traces here. Then now you have to use a few extra things like Chebyshev density and so-called Brouwer-Nesbit theorem to say that traces determine representations uniquely. But that's how this equivalence works. There is a little bit of a catch in that I've only explained to you what happens when P doesn't divide N. So actually, formally from this, the isomorphism of Galois representations actually only tells you an equality of incomplete L functions, where you throw away finitely many Euler factors. There is some subtlety to understanding the leftover Euler factors, but I'm going to sweep that under the rug, and I'll just put a little bit of an asterisk here to let you know that you should be a little bit careful. But that this equivalence is not so, I mean, this is a fairly known thing. But where there's really a jump is if I take these two conditions that are easily seen as being equivalent, and these two conditions that are fairly easily seen as being equivalent, where's the bridge between them? And the point here is that Shimura, building on work of Eichler, sort of showed that this Jacobian decomposes as a product over some equivalence classes of modular forms. Let me not be too precise, where A sub f is an abelian variety associated abelian variety of dimension 2 times the degree of kf over q associated to a new form f. Strictly speaking, it might be a new form of smaller level, but let me, again, I'm going to sort of omit some of the details. And we have an embedding of this number fields into the endomorphisms of A, F, tensored with Q, where KF is a Hecke field. Of F. And what do I mean by associated? Well, what you get is that if I do the point counting on the abelian variety, this is P plus 1. Sorry, this isn't quite right. Well, let me just admit this. Let me just say the point count, this AP of F, for the elliptic curve is exactly what I wrote before. This is actually equal to the pth eigenvalue of this modular form. Okay, and so this fact, and also the L-adic Galois representation, LFL, is the L-adic Gal rep on the Tate module of AF. Okay, so from this, so the point is, if I have a surjective, oh, these are simple. Sorry, this is a, I forgot to say this is a useful thing. A simple abelian variety. So the point is that since these are simple, if I have a map from this Jacobian to elliptic curve, it has to factor through one of these simple pieces up to isogeny. Okay, so then, and that simple piece then up to isogeny has to be isomorphic to the elliptic curve. So what we find is that, on the other hand, these simple pieces are exactly the L-adic Galois representation, or equivalently, their L functions, given in the definition of elliptic curves or abelian varieties, are exactly the L functions of the modular form. So basically, each of these, once you have this in hand, versions X or J and L/G are equivalent to what I might call version A, which is that there exists a new form F inside S2 gamma 0n with rational Hecke fields right? Because if it's a rational Hecke field, oh, sorry, I made a mistake here. Sorry, this is of this dimension. I was thinking about the associated, sorry, here when I wrote 2, I was thinking about the dimension of the associated Gauss representation. So the abelian variety has dimension exactly equal to this. Yeah, okay. So if I have rational Hecke field, that exactly tells me that this piece is dimension 1, i.e. it's an elliptic curve. Rational Hecke field such that this elliptic curve associated to it is isogenous to E. Okay, so that's the state of affairs over Q. Are there any questions about this? Okay, great. So let's move on then. So what I want to talk about now, the purpose of my talk is to focus on totally real fields, but I'm going to indulge myself a little bit. And I'm actually going to talk first a little bit about general number fields. Because the point I want to make here. So general number fields and version L. This version L actually makes sense for any number field, in fact. We can pose this question. So let's say F equals any number field. Okay, so then the objects that replace modular forms are so-called automorphic representations. So this was talked a little bit in Raghurang's talk. And so I'll try to be a little bit sort of brief, and I'm just going to say roughly what these things are. So you can define sort of cuspidal automorphic representations. Say pi of GL2 A sub F. And I'm just going to state some of the properties, is that they decompose as an Archimedean component that I'm going to call pi infinity tensor. So this is some representation. It's going to be infinite dimensional on a big vector space, but you can write it as a tensor product of vector spaces. And then over all the finite places of your number field, it's going to be some sort of what I'll call pi v, such that, well, so 1 for any embedding of F into the complex numbers, there exists canonical differential operators we'll call this, say, omega tau and z sub tau acting on pi infinity. You can think of these things, these differential operators, as somehow acting on pi infinity by scalars. Sorry, by scalars. So these representations will be irreducible, and there's some sort of Schur's lemma argument that says that these differential operators can act by scalars. And these are sort of like coordinates that tell you what's happening at pi infinity. It's a way to kind of label them that you should think of as being analogous to the weight of a modular form. And so we say, and I'll just say a couple of words, I mean, maybe very quickly, where these come from. This Z sub tau is an action of the center. So this is really something that's detecting a central character of the representation. This is a little bit more serious, but this is the Casimir element for SL2, if you're familiar with Lie algebras. So this is the Casimir for SL2, and this is just the center of the Lie algebra of GL2. Okay, and we say pi is, I'm going to put something in parentheses because strictly speaking, you should say this, but I'm not going to for this talk to shorten things. Say it's regular algebraic of, but I'm going to abbreviate this into just saying weight 0 if this scalar, so I said they act by a scalar, act by 0 for all time. So this is what I'll call, so this is the condition on this cuspidal automorphic representation. And I'll say brief in a minute that this is analogous. You should think of this as being analogous to saying the modular form as weight 2. There's a little shift in normalization when I say weight 0, but this is a convenient normalization for the general number field case. Okay, so if these canonical differential operators act trivially, we say that this is a sort of regular algebraic of weight 0. Okay, 2. Another property is that for all but finitely many v, not dividing infinity, pi v is unramified. So actually, I probably should have said, maybe actually I should be a little bit more clear. So pi v is a representation of GL2 of FV. Sorry, I forgot. I want v not dividing infinity here. I want to stick in the, so for v not dividing infinity, pi v is a representation of GL2 FV. And for all but finitely many v, pi sub v is unramified. Or what do I mean by that? This means that if I take the fixed vectors, so let me just for ease of notation, let's let kv be GL2 of the ring of integers of FV. Then to be unramified means that the pi v has fixed vectors under this. And in fact, what you can prove is that if it has fixed vectors, it's at most dimension 1. And moreover, so thus, for such v, so we have double coset operators. So we can form a double coset operator. It's TV, and I can take a uniformizer at V. So let me just add in this pi sub V is a uniformizer. And another coset, double coset operator. I take the scalar matrix. These two double coset operators, so this is defined in the similar way that Hecke operators are defined on modular forms, where you decompose this double coset in terms of single cosets, and you take an averaging. So they act on this space, this k-fixed space, but it's one-dimensional. So if they act, they have to act by a character. They're just by a scalar, right? So this act by scalars, let's call it, say, little tv and little sv, complex numbers. And then third point I want to state is that, again, in this picture, we have an L function. And in fact, it's entire. So it has entire analytic continuation, et cetera. So somebody's asking what general reference for this general version. Oh, that's a good question. I mean, I would say somehow, okay, maybe let me come back to that in a second. This is a very good question. So let me state, let me come back to this. Okay, so we have an entire L function. L pi s such that, and this is defined kind of similar to the modular form case, such that for V not dividing infinity, unramified, the local factor of this L function, this is 1 minus TV times the norm of V to the negative S plus SV times the norm of V to the negative 2s. Yeah, inverse. Okay, so these are just some properties of Cospedal automorphic representation. So I want you to think that it's made up of local data. There exists some notion of being what I call weight zero, but as I'm going to say in an example, this is the analog of a weight 2 modular form. And they have Hecke eigenvalues at all but finitely many places. You can form an L function that has the same kind of general feel as the one for modular form, where it's used Hecke eigenvalues. So let me give the example. We call this example, let me label my examples because I might want to reference them. Example 2.1. So let's say F equals Q. And F inside S2 gamma 0 n is a new form. Then, so what you can, so that is something, this takes a bit of an argument, but you can show that GL2 of the Adels over Q. Oh, sorry, let me sorry, I want to introduce something first. So I'm going to define a sort of adelic version of gamma naught. Let's set U naught of n to be the set of matrices A, B, C, D inside GL2 of, the profinite completion of the integers, which if you like, which I certainly like to, you can think of it as the product over all primes, GL2 ZP, and such that C is congruent to 0 mod n. Okay, so then this is only a condition at the primes that divide n. It's no condition otherwise. So we can show that GL2 A sub f is equal to the product of GL2Q, GL2R plus, where the plus means positive determinant, and this group U naught n. That these things generate the entire Adels. So you can define, so let's say you write some G here as equal to, I'm going to write it as gamma, I'll call it G infinity U. So we can define a function, let's call it phi sub f. This would be a function on the Adels invariant under the diagonally embedded GL2Q by phi sub f of G. Oh, well, let me write it to be more explicit. If I've written my G as G infinity U above, I define this as being the determinant of G infinity J, G infinity acting on I. So this is a standard cocycle on the upper half plane. And I take G infinity acting on I valued at F, where here, I'll just recall J of A, B, C, D acting on I, or acting on Z, say, is equal to the standard action AZ plus B over CZ plus D. Okay. So this funny formula, but the part of the point here is that this is actually well defined. So I've said that this is the product of these three groups, right? But I mean, maybe you can write these things in multiple different ways, and it's certainly true you can. But why is this well defined? This is well defined since if I take the intersection inside GL2Q with the group generated by GL2R plus and U naught of n, this is exactly equal to gamma 0n. Right, because these will be things with positive determinant, they have to be rational entry, and they have this congruence mod n, and it turns out these are just going to be things in SL2Z mod n. So the invariance of the original F under gamma naught n implies that this function I've defined in this way will be well defined. And okay, and then if you do this construction, the great thing is that then, well, phi sub f generates one of these gadgets I said above, a cuspidal automorphic representation. Let me call it pi sub f, which we can then decompose as the infinite part and then over all primes PFP, such that let's see, pi f is weight 0 in the way I described above, and for all p not dividing n, pi f p is unramified with pp equals the Hecke eigenvalue in the way I described on the automorphic form is the Hecke eigenvalue for the original modular form. And this other Hecke eigenvalue is just p, this one coming from the diagonal matrix, pp0. And moreover, at the other, so in particular, this tells you that the L functions are equal for all these primes, but in fact, the entire L functions are equal. So the construction for in this general case recovers the classical situation here. Okay. So now let's go back to generalities, and then I'll answer the question in the chat once I finish. So now, if E is any elliptic curve, over a number field F, we say E is modular or automorphic if there's one little catch. This doesn't happen for totally real fields, but I'll point it out for the general number fields. If E has Cm by a subfield of F, okay, because if this happens, then the L function of E is going to be given by a Grossen character in this situation. So this is sort of an easy case that you can always handle. Or there exists a cuspidal automorphic representation pi of GL2 AF such that we have an equality of L functions. Operate weight 0. Sorry, I want to specify weight 0. Weight 0 representation pi of GL2 AF such that L S equals L pi S.
Can you say why subfield of F and not a bigger field?
No, because okay, the rough reason why is that if it's by a bigger field, then one way to think of it is that the Galois representation associated D will be irreducible in that situation. And so then it actually will fall into the second case.
Oh, okay.
That there will exist this thing, right? The only thing I want to sort of be worried about is that this doesn't apply in the situation where the L function of E is actually a sort of a product of 2 degree 1 L functions, or the Galois representation is reducible. Then you won't be able to, it won't be a cuspidal thing. You could say that there exists some weight 0 automorphic representation, but it would be an Eisenstein series at this point. And I didn't want to get into that. I hope that answers the question.
Yes, thanks. Yeah.
Yeah. Okay. Yeah, okay. And so then to go back to the questions in the chat, asking for a reference of this. Well, one thing you could sort of look at. So for instance, yeah, as far as references go, for this example, there's this, the fact that going from modular forms to these cuspidal automorphic representations, there's this really nice little book by Gelbart that I think is pretty classical, Automorphic Forms on Adele Groups, that I very much like. But then, a larger book that is a little bit more extensive is Bump's book, Automorphic Representations, and that will discuss a little bit of this. Now, he doesn't mention elliptic curves specifically, but he does talk a little bit about the philosophy of Langlands, about how motivic L functions should be equal to automorphic L functions, and that's what's going on here. And it's the case that really all I'm doing is I'm applying the philosophy of Langlands that says, L functions coming from sort of varieties or irreducible compatible systems of Galois representations or pure motives, etc. Insert your favorite arithmetic description here, should come from L functions of automorphic or representations. And I'm just sort of using the knowledge that for an elliptic curve, because of the sort of the nature of it being an abelian variety or its sort of so-called Hodge type, I should be looking at something for GL2, and the condition at infinity should be this, exactly this condition. Let me just say as a bit of an aside too. So, in earlier talks for Hilbert modular forms, we were discussing things being discrete series at infinity. So this does recover the description of discrete series of weight coming from a Hilbert modular form of parallel weight 2 in the case where F is totally real. But this description also works for a general number field for where the elliptic curve should come from. Okay. Are there any questions about this? Yeah, so something
yes,
I just want to
I was wondering if whether there was a reference that would describe a little bit more these operators in the case that you're not in a CM situation. I mean, CM about the field, a non-CM field.
You mean what
happens?
Operators?
These no, the omegas, omega tau, and whatever.
Yes, but I think for any embedding, right, you have either GL2R or GL2C under this embedding, and so you just look at the complexification of its Lie algebra, and this will be. And once you fix an embedding, you just have something that looks like the.
So it's
Lie
purely
algebra.
the Archimedeans.
It's just Archimedean. Yes, exactly. I'm just looking at the Archimedean when I'm doing this. Exactly. That's right.
Thank you.
Yeah, you're welcome. Okay. Are there any other questions about this? Okay, great. So again, and now let me also say that for a general number field, I've just said what it means to be modular. I've given you no indication of whether you could ever dream to prove anything. This is just, you can make this question well posed now. Okay, so now let's go. Let's talk about. So this was just the L function version. Let's talk about other versions over totally real fields. Sorry, I want to. Okay, but I'm going to put a question mark here because it's a little subtle. Things don't work out as well as you might hope. Okay, so for now, F equals totally real. AF will be the Adels of F, as before, which remember, let's write as AF. We have an infinite part times a finite part. And let's say I take U inside of GL2 AF away from infinity, open compact. Yeah, let me see this. So there exists a smooth quasi-projective variety y of u over q such that its complex points are equal to the double coset GL2Q mod on the left, GL2 AF, modulo U, K infinity, and then R. Let me see, am I saying this? Get myself a little bit worried here. I'm going to say Z infinity. I'm going to say Z infinity, where here K infinity equals the maximal compact of GL2 F tensored with R, and Z infinity equals the center of the same thing. Okay, so example. Let's just see what happens. So example 3.1. So F equals Q. So let's go to example 2.1. Then because, so using the fact that GL2, as I mentioned, the adels here equals GL2Q, GL2 R plus U naught of N, and the fact that GL2 R plus modulo this maximal compact K infinity, this is just O2, 2x2 orthogonal group. And then the center, this is isomorphic to the upper half plane, right? You just act by Mobius transformations. The stabilizer, there's a little bit of a catch in that. Sorry, this is SO2, right? So you act by Mobius transformations on the upper half plane. The stabilizer exactly this group. So you get a homeomorphism of manifolds. You can show then that this Y of U naught of N, as I described above, is exactly the modular curve Y of N we had before. This is some generalization of modular curves now for totally real fields, where it's better to use the adelic description. Yeah, particularly if your number field has strict class number bigger than 1. And I think this was explained in previous talks. Okay, so let's go back to the situation. Actually, no, let me do another example. It's a little bit more representative because I want to use this later as well. Example 2.2. Let's say F over Q is real quadratic. And let's say the strict class number equals 1. And yeah, let's say U naught of N defined analogously. Right, sort of the bottom left entry of matrices congruent to 0, modulo some. You could take some integer n, or you could take some ideal now in your totally real fields. Then, and let's say I set now my gamma 0n to be defined as being the intersection inside GL2F. Sorry, we need some more room. It's being the intersection GL2F with the subgroup GL2 are positive, or I mean totally positive elements generated by this U0 of N. Then let's see, the complex points, what you see is the quotient of the upper half plane times itself by gamma n, gamma naught of n, this discrete subgroup inside GL2. This will be an OF totally positive. And now this acts by mapping it to GL2 R plus times GL2 R plus, which then acts on the upper half plane times itself, each copy, where this sends an element gamma to you take one embedding applied to gamma, and you take the other embedding applied to gamma. So our HOM FR equals sigma 1, sigma 2. This is another example, right? You get some sort of quotient of the upper half plane squared. And in general, at least if you have strict class number, well, in general, what you have is you have, D many copies of the upper half plane, where D is the degree of the totally real field. And then you have some finite number of copies of these, where it depends a bit on the strict class number and also depends maybe on what you take here. Okay, so now that we have some objects that are the parallel of modular curves, you could ask, so now say we have E over F, an elliptic curve. Okay, let's say we form this subgroup where maybe, let's do the same thing as before. We take some conductor of E. And maybe you just want to formulate this sort of so-called version X over this totally real field. Well, first there's a little confusion that happens, which says, well, this analog of the modular curve is defined over Q. Okay, that's a little strange. It's defined over a different field than E, but okay, maybe it's not too bad. You just view it as being defined over F. Okay, I mean, you can think of it as an F variety then. Okay, but now there's another but. So in formulating this previous version of the conjecture, we compactified the modular curve, right? We compactified Y naught N to now in this situation, there's no canonical choice of a smooth compactification. Does not have a canonical smooth compactification. I mean, it has smooth compactifications, but there's no canonical choice. It also has a canonical compactification, but it's very singular. So you get a little bit nervous. But let's just say we forge ahead. Let's just choose one. Because we're going to see the things are going to go terribly wrong in a second. Anyway, so it doesn't, these are minor issues. So now I want to get to the big but. Okay, so. And let me just ask.
Yes. Hi, is n integer or is n a real quadratic integer?
No, this could be this could be an ideal at this point.
But then still yu gamma naught n is defined over Q.
So exactly, I want to say hold on a second. Is it defined over Q? No, I think not defined. Will this not be defined over Q? No, maybe you're right. Okay, it will. But so hold on. If the determinant maps is still surjective, do we not get something that's defined over Q, or is that wrong? No, I don't think it's right. Okay. Let's just say, let me be a little bit loose then and just say sum n. Sum n. Let's say sum n is an integer. Sorry, let me be a little bit, you're right. I need to be a little bit careful here. So let's just do this for now. Because things are going to go wrong for much worse reasons anyways. So let's just say I want to do this. Then this is defined over Q. You're right that in general, you have to be a little bit careful of where this is defined over depending on the level. Here. Sorry, thank you for that. Any other questions, comments, or corrections? Okay, so, but now here's the real problem. Let's say I have surjective. Let's say I take the same kind of definition, right? Which remember, because this is a complete curve, if this is a compact thing, this is just being non-constant. Let's pull back. The invariant differential. On E to X of U. Okay, sure, we can do that. And let's say to simplify things, say we are in example 3.1 above, or 3.2. So where real quadratic strict class number is 1, then pull it back further to the upper half plane across the upper half plane. Okay. But if we do so, we can write it as F1 dz1 plus F2 dz2. Okay. But now you do the same sort of thing as you do for modular curves, and you say, well, if I had this differential here and I pulled it back to this upper half plane, it has some invariance under the action of this discrete subgroup that's acting on this, right? Just because of the way, since it's an invariant differential, it has to be invariant under that group. And we can just compute how that group acts on dz1 and dz2. But what that's going to imply, this is where things go a little bit different, is F1 and F2 are Hilbert modular forms of weights. Now notice that the first embedding acts on this Z1 and the second embedding doesn't, and vice versa. So what you get is that they have weights 2, 0 and 0, 2. You do the same computation as you do for modular forms. It's just that only one embedding, for each of them, only one embedding matters. But there are no such Hilbert modular forms. Just like with the case of modular forms, you have to have all weights bigger than or equal to 1 to have a non-zero space. So this is a contradiction. This just doesn't work. So you run into a problem that this version, and similarly, I mean, so anytime you have a smooth projective variety, you have something that is an analog of the Jacobian. It's called the Albanese. So you can form an analog of our version J of the conjecture, but it won't work in this situation. So what's the fix? So we need a curve. Right. If you wanted this to work, you need a curve. So here's how you can do this. Say D is a quaternion algebra over F such that D tensored over F with respect to some embedding of R is 2 by 2 matrices for some tau embedding F into R. And then D tensored over F sigma R is division for all tau not equal to sigma. Okay, so then similar to above, so replacing GL2 AF with D tensored AF cross, we can formulate analogous, we get a curve YD of U, let's see, over F. And now let me just put an asterisk, this may be for appropriate U, probably. But certainly for the U's we care about, this will work. And with compactification, so this is a curve, you can find a nice smooth compactification easily. In fact, in this situation, I mean, it will already be compact. So maybe with compactification, well, let me, because this will, if I'm including the case Q, we need to compactify it. And in fact, these are equal. This is already compact. So in fact, XD equals YD if F is not Q, which is a situation we really care about. It's already become packed. Then we can ask for X du surjecting onto E, and similarly, where this is equivalent to saying it's Jacobian, right? I.e. the analog of versions X and E. You can do the exact same thing. And you can also mimic Eichler to get simple abelian varieties A sub pi corresponding. Now here's sort of a little bit twist to weight 0 cuspidal automorphic reps of. But now it turns out that, and maybe naturally, right, because we're looking at this group, so that you can form an analogous definition as to GL2, but you get cuspidal automorphisms of this group. So you think to yourself, wait a second, I thought we were trying to look for Hilbert modular forms here. And well, yeah, I mean, but what arises naturally now that we're using the curve defined by this group is what we do is we get the automorphic objects corresponding to this group. But then you use the theorem, Jacquet-Langlands, is that there exists an injection between, let me call this capital pi sub d. Let's see, I don't want to say, no, maybe capital pi parentheses d is how I did in my notes. This will be weight 0 cuspidal automorphic reps of D tensor. They do this for other so-called weights, but I just want to stick in this case to, let me call this map JL, weight 0 cuspidal automorphic reps of GL2 AF. Let me call this set capital pi of GL2. Or maybe, sorry, I'm running out of room. Let me call this capital pi GL2. It emphasizes the number over the number field F, such that, well, it has the following property. First, if let's say pi inside capital pi of D and V place such that, say, this quaternion algebra is unramified, and to FV, well, then this group associated D just looks like GL2FV. So then the point here is that if you take the Jacquet-Langlands transfer of pi and look at its place at V, it just recovers itself, right, as a representation of GL2FV. And that tells you what happens since this quaternion algebra is ramified only at finitely many primes. This tells you what happens at all but finitely many primes. And then there's something called strong multiplicity that uniquely pins down this image. There uniquely pins down what this object is. But let me say there's a little bit of a twist, and this is sort of subtle, is that the image of JL is not everything. This consists, this is not surjective. So I can tell you what the image is, but maybe I haven't defined the objects, so it's maybe not as crucial. Well, let me say this consists of all the pi equal to all v less than or equal to infinity. Let me write it this way. Since I'm running low and since I'm basically out of time, actually, let me just state sort of the consequence. So let me just say can characterize the image of JL. Okay, so you might say, okay, so we're done, right? So what I said is that, well, you can find these Shimura curves, you can formulate the equivalence of this, version X or version J using these Shimura curves, and you can describe these objects by using Jacquet-Langlands in terms of Hilbert modular forms or cuspidal automorphic representations of GL2. So you might say, we're done, right? Well, no, not quite. So there's something funny that happens here, and it's a thorn in many people's sides, is there's a simple fact, right? D must ramify at an even number of places of F. So if you're in the situation where F over Q is even, and now this is something that I didn't quite explain when you characterize the image. One important consequence of this is that if you're in the situation where this is even, oops, and pi inside, let's say I take one of these weight zero cuspidal automorphic representations of GL2F, so this is something coming from a Hilbert modular form up to twist. If this is unramified at all finite V, then pi is not in the image of JL for any D. You cannot realize it as a Jacquet-Langlands transfer. This never happens. And so let me just finish by saying here's an open problem. And let me say, as far as the elliptic curve modularity, if you just go back to the L function, then elliptic curves with everywhere good reduction should correspond to such pi. So maybe that's worth a remark. So remark an elliptic curve. And these exist over totally real fields. They don't exist over Q, but they exist over totally real fields with everywhere good reduction should correspond to such pi. So let me just finish. Sorry, I'm a couple minutes over. This is still open. Is let's say F over Q is even. Pi, one of these objects I defined above. So pi, let me say weight zero. Since I'm stating the open problem, let me be more precise. Weight zero, cuspidal automorphic representation of GL2. It's totally real field. And unramified at all finite V, then we want to show there exists, and let's say the Hecke field, say Hecke eigenvalues. Let's even restrict to this case with rational Hecke eigenvalues. So the open problem is show there exists an abelian, an elliptic curve. So the Eichler-Shimura construction, a pi with the L function of the elliptic curve equal to the L function of pi. I still don't know how to do this. This is open. It's sort of amazing. This is, and let me say it's even more frustrating than what I've written down. There's a sort of folklore argument that I first saw written in a paper of Blasius that basically shows for such objects, you should never be able to find it in the cohomology of any Shimura variety. Not even just restricting to things like these Hilbert modular varieties I've defined. They just shouldn't come from Shimura varieties at all. And that's the only trick we know, honestly, to build such algebro-geometric objects associated to automorphic forms. So it seems we're really in the woods. But on the other hand, you can actually check some of these things computationally. You can actually go out and search for your favorite elliptic curve that's unramified everywhere, or your favorite, or in this direction, your favorite modular or Hilbert modular form of level 1. And if you find one that has rational coefficient field, then you can start looking for the elliptic curves that have everywhere good reduction, and you can actually match up computationally in specific cases. But we just don't know, where to look for them in general. So yeah, since I'm over time, let me stop here. Yeah, thank you.
So let's thank Patrick for a very nice talk. Okay, are there any questions, comments, remarks? Yes.
So I was wondering whether for any number field you are expecting E modular with the first L function version.
Yes.
And in this version, what do you expect?
I mean, the thing is, it works if you're over a totally real field and your elliptic curve, say, if either the degree, so to recap, if the degree of the totally real field of Q is odd, then you can always view it. You should always be able to view it as the surjective image of a Shimura curve. Or if the elliptic curve, say, has a potentially multiplicative reduction at any place, then you should be able to view it over as an image of a Shimura curve. But if you're in the situation, say, where the degree of the total real field is even and you have good reduction everywhere, then you shouldn't.
So the formulation works only with some conditions, and then you expect it to be true, right? Is that?
Yeah, exactly. Okay. That's right. And that's the really strange thing, is that, like, even to formulate it, if you have certain conditions, you can. But if you don't have those conditions, we don't know how to. Moreover, there are arguments that say you should not be. It shouldn't be possible, basically.
So actually, I'm wondering, and I see the Professor Brumer is in the audience. Maybe he can shed some light on this. There was, I'm interested in the historical thing. Taniyama, when he first formulated the, Shimura-Taniyama-Weil conjectures, he sort of said that any elliptic curve or any number field should be sort of be describable by some automorphic functions. So that time, it was vague, but people then said that that's too much generality, it won't work. And I am not sure with what you said. So I'm just curious about, what is the point where people were objecting, and then Shimura had made a precise conjecture over Q and so on, but there was some strong objections in general. So maybe I'm just curious about the situation.
Yeah, I don't know the history of what Taniyama first said. And my understanding is when I read it a little bit, it was maybe sort of imprecisely stated. And so I didn't find I was able to digest it in a way that sort of resonated very well with me.
Right. Professor Brumer, do you have any comments on that? You probably know this.
Well, there was a controversy that was raised by Lang. I don't remember exactly when, but where he even objected to Shimura having made the precise conjecture. And I don't want to go there.
No, I'm not interested in the who did what, but I am interested in
there was no precise. I don't think that there was anyone who made a precise conjecture. Maybe the closest thing was there was a spring election note by André Weil, but I'm not completely sure how precise that was either. I would like to just double check. Is it expected that you always have a Hilbert modular form? I'm assuming F is totally real. Is it expected that there's always a Hilbert modular form of weight 222 that corresponds to every elliptic curve, and vice versa? Or
Yes, yes, exactly. I mean, so something I guess I forgot to sort of state, I meant to at least state sort of out loud, is that this condition of being regular algebraic of weight 0 is these all arise from Hilbert modular forms of parallel weight 2.
okay, so what's missing is the nice interpretation where you cover the elliptic curve by an abelian variety.
Yes, exactly. That's what's missing. And something that I'd hope to say also, but I didn't go over time, maybe is worth mentioning quickly now, is that there was also this Galois interpretation. And that actually does hold a total generality over total real fields as well, because what you can do is you can always find congruences to a situation where you're in this situation where you can apply Jacques-Langlands. And so, yeah, we have, to recapitulate a little bit, was we have the L function works for any field. The Galois representation version works when Galois representations are constructed, because they're essentially equivalent to the L functions. And for totally real fields, the Galois representations are constructed in total generality for Hilbert modular forms. But the geometric definition only seems to work when your elliptic curve should come from a Hilbert modular form that admits a Jacques-Langlands transfer to some division quaternion algebra, such that it is split at precisely one real place. This is the condition, because this is what guarantees you have a curve. If you can't come from such an object, then we don't know how to do the geometric description of being modular.
By the way, how general, I'm going to show my ignorance, but I'm used to it. How general is a Jacques-Langlands? Does it work when you're not totally real or a CM field?
Let me make sure let me think about this for a second to make sure I say something careful. But yes, I think it works for any number field. And let's see, I don't remember if, I think probably Jacques-Langlands did it in that generality, but
okay.
I haven't actually looked carefully at their paper, to be honest. Have looked, and I think this also generalizes to higher rank in Arthur Clozel, their book. You can do GLN as well. But I don't think there's any need for, I don't believe there's any need for this to be totally real or CM for this to work, because their proof, I think, is quite, it's just a trace formula thing. They don't use any algebra, geometric, anything. And I think that there's no limitations for the trace formula in that way. Again, I wouldn't, that's what I believe.
Yeah, no, I just was wondering.
Yeah.
And then what about the Bianchi forms, let's say for if F is totally just an imaginary quadratic field? Do you have any picture of this type or not?
No, I think not. That's even weirder, because, they're in a situation where these things aren't even algebraic. So it's not. Yeah, this is something that's, a really good point to emphasize is, like I said, this L function, sort of makes sense over any number field. And you could try to play the same game as I described here, where F is not totally real. And you could say, take this same double quotient, and you do get some sort of space where it can be its cohomology can be described in terms of automorphic forms. And this is in a previous lecture, at least in the total real case. But the problem is that this thing is no longer a quasi-projective variety.
Right.
This is really, over imaginary quadratic fields, what you get is some sort of quotient of a hyperbolic 3 space, or maybe finite many components. And these things are really just real manifolds. So you start asking yourself, well, what does it even mean for a map from the real manifold to this elliptic curve? And I guess you could ask for it, but you're probably not going to be leading to any structure that somehow is interesting. So yeah, that's in a situation where the motives are even more mysterious.
Yeah, thank you.
You're welcome.
Are there more questions? So I have a couple of questions. So one was about this open problem that you stated. So basically that means for those kind of Hilbert modular forms, the Eichler Shimura is not known, right?
Well, depends on what you mean by Eichler-Shimura. I mean, so yeah, so like the Eichler-Shimura construction of saying you have some sort of Hilbert modular form, you can construct an abelian variety with this property.
Yeah.
So people often refer to this as the Eichler-Shimura conjecture, even though I'm not sure if they ever wrote it down as a conjecture, but as a natural conjecture to make based on their construction.
Right. But if the degree is odd, then
then you're okay. Exactly right. Because now what I didn't state here is, I mean, so to be a little bit precise, what is the image of this? It's exactly the automorphic representations that are so-called square integrable at any place at which D is ramified. So, what that means is that for any finite place at which D is ramified, the image here has to be either a twist of the Steinberg or supercuspidal. And so what that does is that forces from the Hilbert modular form language, that forces the objects to be new at that prime. It has to have that prime in the level and be new at that prime. And so whenever you're in such a situation, I mean, but it's a little bit more refined in the sense that if you're just talking about levels, you can have things like ramified principal series on the automorphic side that are still not in this image. So it's a little bit more, it's better to think automorphic language. So they're just never in the image of this Jacquet-Langlands transfer. And those are the only situations we know how to construct these abelian varieties.
Right. And so what is the latest progress on establishing the modularity over totally real fields or over number fields?
I think, let me say, I think that's coming up in a future talk, right? If you want to establish the modularity, and it's known for all real quadratic fields. It's known, I think, for maybe real cubic fields as well. And it's known that over any general totally real field, there are most finitely many exceptions to it. So there's certainly a lot known over totally real fields. Over other things, it's a little more mysterious. Over CM fields, it's known that they're all potentially modular. You can do things like show that over CM fields, positive, under some technical conditions, a positive proportion of elliptic curves are modular. That's a sort of something that can be proved nowadays. Over other number fields, though, things are just sort of, you lose almost all hope. Except for there's a very, very interesting results by Boxer, Caligari, G, and Piloni. That's a result of their potential modularity of abelian surfaces. You can prove that elliptic curves are modular over fields that are of the form quadratic extension of a totally real. So they don't necessarily have to be CM, but if you're a quadratic extension of a totally real field, any elliptic curve over such a field is potentially modular. And the way they do that is they take the restriction of scalars to the totally real field, and then they apply the modularity to the abelian surface.
I see.
Yeah, it's pretty amazing. But if you want to say things over, number fields that are not of that form, then I think it's hopeless. The only examples, I mean, certainly things like CM you can do easily. And then there may be sporadic examples people have computed just to show that this exists, but I think there's no hope of actually proving it.
Okay, are there any more questions, comments, remarks, anything?
So just curious, so if you are just interested in potential modularity, can you get rid of, then can you do geometric? I mean, for example, it's even restriction then doesn't matter, right? Then can you do it geometrically?
Well, it's a little bit strange. What did it say? So can you do it geometrically? Yeah. No, it's a little bit tough because I don't see the even thing going away, because if you base change, if you start off with a field that has even degree over Q and you base change, you're still going to be even degree over Q.
Oh, that's true.
Yeah, exactly. It's the opposite, that somehow.
Exactly.
So, but that's actually a very good question, is because you might hope you could do something. I mean, what is base change? Base change is some instance of functoriality. And so you might hope, well, maybe there's some fancy functoriality that maybe we can apply to get ourselves out of this bad situation. But as I mentioned briefly, there's a sort of folklore argument that I found, and there's a paper of Blasius about Hilbert modular forms and motives, and maybe the absolute Hodge conjecture is in the title, where he says it's a folklore argument, but he sort of sketches it to say that if you have such an object, there should not be there should be no Shimura variety at which you could view this, the sort of the motive it's supposed to generate in its cohomology. And so it seems then you're hopeless to try to reduce yourself to any Shimura variety using any sort of functoriality. And so there's somehow sporadic points out there in the land of motives that we don't know how to patch together.
Yeah, thanks.
So yeah, are there any more questions, any comments, remarks? Yeah, I guess we are out of questions. So let's thank Patrick again for a very nice talk.
Thanks, Shaunak, for chairing also. And thanks, Patrick, for the wonderful talk and exposition.
Thank you again for the invitation and for everybody coming and asking great questions.
So I guess
Ganesh, you can maybe stop the live stream.
I suppose the recording is going to be available on YouTube, and maybe the notes will also be available, right?
Yeah.